Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers. Because once we do, we'll be able to put a donate button and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD and working on a product to help people overcome these problems because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you.
Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast, now part of the Finding Genius Foundation. Speaking to Gregg Beckham, he's a senior research fellow at the National Renewable Energy Laboratory. And we're going to talk about plastics, not just recycling, but what's called upcycling and conversion of biomass to fuels. So should be a very, very interesting call. Gregg, thank you for coming.
Thanks, Rich. Thanks for having me today.
Well, tell me a bit about your background. How did you get to where you're at NREL? And then I want to ask you about your current work.
Great. So I'm a chemical engineer by training. I did my undergraduate degree at Oklahoma State and master's and Ph.D. at MIT, all in chemical engineering. And I worked during my Ph.D. in the petrochemical industry, in the pharmaceutical industry, and in food as part of a program at MIT. And through those experiences, I knew that I really enjoyed process design and process engineering, but I always had a really strong desire from a career perspective to work in energy and environmental applications towards sustainable energy and environmental pollution remediation and things like this.
Yeah, I wanted to do some of the same work, and I remember I got a bachelor's in chemical engineering, but it did seem like unless you get a PhD, you kind of do more field work and just compliance instead of the research behind it.
Yeah, absolutely. It's been I've been really blessed in terms of being able to apply things picked up during a PhD to energy and environmental applications in a research context, especially.
So tell me about some of the projects you're working on at NREL right now, please.
Yeah, absolutely. So one of the primary projects that we work on here at NREL in our group, and as part of a broader program, is the BOTTLE Consortium. And so I'm the Chief Executive Officer of this BOTTLE Consortium. BOTTLE stands for, it's an acronym that stands for Bio-Optimized Technologies to Keep Thermoplastics Out of Landfills and the Environment. And it's a 10-member consortium that's funded by the U.S. Department of Energy. And in the BOTTLE Consortium, we focus on two primary research areas. The first is how do we deal with and recycle and upcycle today's plastics? And, really focusing there on, how do we go beyond current recycling approaches that are used today, like mechanical recycling, which is how when we put, like, say, single-use beverage bottles into recycling bins, if they're recycled, they go through mechanical recycling. That's great, and it's definitely a, at-scale technology, but there are many other plastics out there that are not recycled at all today, right? And in some cases, even the ones that are recycled end up going into, say, a PET bottle, polyethylene terephthalate bottle, like a single-use water bottle or single-use beverage bottle, will end up going into textiles like clothing or carpet, which will eventually end its way in the landfill. And so in the BOTTLE Consortium, what we and our team members are trying to focus on is, first, how do we basically widen or increase the amount of plastics that are able to be recycled through selective technologies that can break plastics down into molecular intermediates and then build them back up either into the same polymer they were before of the same quality or upcycle them into new materials that are higher value that can be used for other applications. And in that way to
Yeah.
incentivize reclamation of other plastics.
For basic terminology, I've heard of recycling, of course, downcycling, and upcycling. Can you just give a quick primer on the three terms?
You bet. So to me at least, and we've proposed these definitions in the literature, downcycling is the creation of, you take a waste plastic and you create something of lower value, right? That is downcycling. True recycling is you take a plastic in and you make the same plastic out the back end of your recycling facility. So such that a bottle goes back to a bottle, right? That's true closed loop recycling. Upcycling, on the other hand, we define, and many others in the community define as, again, you take in a waste plastic into your facility and then you convert it to something of higher value than that waste plastic itself. And so, for example, turning a single-use beverage bottle into a wind turbine blade, or into a snowboard or a surfboard, or into part of a panel of a vehicle, and things are on a car, for example. So things like this.
So in terms of level of difficulty and amount of inputs required, is downcycling easiest than upcycling?
Yeah, that's a great question. In the context of the way that plastics are, the few plastics that are recycled today. So again, using the example of your single-use beverage bottle going to textiles or fiber that goes to a carpet, right? I mean, that's a very well-established technique. The nice part about it is it is well-established. It's cheap and it's easy to do, and it works. It's a good thing. I mean, definitely we should keep using mechanical recycling approaches where we can, but ultimately those materials will end up back in the landfill. Clothing, for example, is put in landfills at massive amounts during every year. And so then the question becomes, for either closed loop recycling or upcycling approaches, can we take those waste, for example, textiles or clothing, and can we break those down into molecular intermediates and then build them back up into either a new beverage bottle or a wind turbine? And almost undoubtedly, the amount of energy input and materials input to do the latter case is probably going to be higher. But that's a really key question that, through technology development, we need to develop, we as the research community, the industrial community, we need to be working on developments of the most efficient recycling, upcycling approaches possible, such that we can actually do this at scale one day and make money, as well as do this in a more sustainable fashion, such that we reduce energy inputs, we reduce greenhouse gas emissions, especially relative to virgin plastics manufacturing.
Well, what is the current state of recycling? Are most things downcycled, or are most things not even touched at all? And then the ones that are downcycled, or what does it look like?
Yeah, great question. We just published a report wherein we looked at plastics in the United States at least, and in recycling rates in the United States at least, and it's below 10%. Most of that goes to landfills. The current plastics that are recycled at large scale are high-density polyethylene. So think of like your plastic milk jugs, for example, that you buy at the grocery store. That's high-density polyethylene mostly. Those can be recycled many times. And then the other, again, primary plastic that is recycled at scale today through mechanical recycling are single-use beverage bottles. And those can typically be recycled once or twice as bottles in a bottle-to-bottle recycling facility. But in many cases, even in the first life, those go into carpet and clothing and textiles as well. And maximum can be recycled 2 or 3 times before the material properties are compromised such that they can't be used in bottles anymore. And so those are really the only 2 plastics that are recycled at scale. But there are many other plastics out there, right? You think about your keyboards on your computer. Think about your toothbrushes, your mini consumer goods, toothpaste tubes and food packaging and things like this. There's a lot of other plastics out there that are not recycled at all.
I would think there has to be trade-offs when recycling, even stuff that's easily recyclable. I've been doing interviews, for instance, on microplastics. So I guess the thought pops into my head is when you recycle a given plastic, does it become more friable and more likely to give off microplastics, or is that not even part of the calculation yet?
Before we continue, I've been personally funding the Finding Genius podcast for 4.5 years now, which has led to 2,700 plus interviews of clinicians, researchers, scientists, CEOs, and other amazing people who are working to advance science and improve our lives and our world. Even though this podcast gets 100,000 plus downloads a month, we need your help to reach hundreds of thousands more worldwide. Please visit findinggeniuspodcast.com and click on Support Us. We have 3 levels of membership from $10 to $49 a month, including perks such as the ability to see ahead in our interview calendar and ask questions of upcoming guests, transcripts of podcasts you're interested in, the ability to request specific topics or guests, and more. Visit findinggeniuspodcast.com and click Support Us today. Now back to the show.
That's a really good question. And in mechanical recycling approaches today, so for example, without saying the company or the recycling facility, we were, and some colleagues were given a tour of what is considered to be a fairly sophisticated mechanical recycling facility. And for their polyethylene terephthalate or PET lines, which is again your beverage bottle type plastic, they make a lot of fines in those processes, like a lot of really, really small particles that can't go back into the recycling, essentially supply chain. And those are put in the landfill, right? And in some cases, literally washed down the drain. And so, there's the current processes aren't perfect, but that's where the technologies, for example, that we're developing in the BOTTLE Consortium can help, because we can take, for example, those fines, those microplastics that result during mechanical recycling that are hard to mechanically recycle or impossible to mechanically recycle, and put those through a chemical recycling approach to be able to break them down and then build them back up to the pristine polymer that they were to begin with.
So what's, now to the projects you're working on, what specifically are you working on? And I just want to ask you more follow-up questions based on that, if that's okay.
Yeah, absolutely. So we're working on several different types of technologies. One is focused on, again, let's stick to the polyethylene terephthalate theme for a little while, PET. And so we work on enzymes, which are nature's protein catalysts, such they accelerate chemical reactions dramatically over non-catalyzed reactions to break down polyester, like you would find in polyester clothing, again in flakes or microplastics that result during PET bottle recycling, from carpet, and from food packaging in many cases, which is also either fully or partially PET. And so we work to develop enzymes that we prospect from nature, like hot springs and other places, to develop industrial scale processes to be able to use enzymes. Think of it like a big washing machine, basically with hot water in it, waste PET plastic, and enzymes that you would dump in that would look like very similar to powdered laundry detergent, which has enzymes in it, by the way. And you could dump that in and you could break down PET plastic, and you can literally watch it. And we've done this with bioreactors. You can watch the plastic literally disappear into the molecular building blocks. And then we recover those and we recycle them into pristine PET plastic. That's one project we're working on. Rich, I can tell you about others if you want to pause there too. Yeah.
Yeah, I got a couple questions about that. So it's successful at bench scale. Has it been, can it be scaled up? I had thought for some reason as a layperson, again, there are a lot of laws that would make it very difficult to ever call a material virgin again and allow it to be used. Is that a factor?
Yes. So there's 2 questions there, right? So one is, can it be scaled up? So there's a company in France, Carbios, that is definitely scaling up this type of technology now with many household name companies even. There are challenges in the way that the community is attempting to scale this up, and what we do here, besides working on enzymes and developing processes, is we do techno-economic analysis and life cycle assessment, which basically answer questions about processes from an economics and environmental impacts perspective, respectively. And there's a lot of challenges in enzymatic recycling of PET, from a waste generation perspective, energy input perspective, and a cost perspective. And so what we're trying to do is tell the research community through these rigorous analyses that are transparent and open to everyone is, here are the innovations needed to do this even better at scale than folks are at least talking about now. And so that's one key aspect of that. The other question you asked, Rich, is about regulatory sort of components of, calling a plastic virgin, virgin-like plastic or pristine-like plastic. And so, Yeah, that's a great question. I'm honestly not the best person to answer that, but I will say that we and many others in the community have been able to break down, again, using PET as the example, to break that down and then repolymerize that into plastic that has all the same properties of the pristine or original materials.
That's great. I've also heard that, when it's not just easy working with, so when, a plastic bottle is made, there's all kinds of other chemicals, and it could be in the thousands.
Yep.
And when enzymatic action especially breaks these down, are you getting just the building blocks of PET, for instance, or you're getting like a witch's brew of different chemicals, and how does that affect your ability to recycle?
That is an excellent question. Certainly, all polymers, plastics, right, that we use as consumers in industry, basically everywhere where synthetic polymers are used, they have additives in them. In tires, there's an enormous amount of carbon black and metal and things like this. In clothing, it can be, multiple percent dyes and pigments and other types of things. And so, and in bottles as well, you'll have the catalyst, for example, that was used to polymerize the PET in the first place in there, as well as perhaps dyes or pigments. And yeah, enzymes, chemical catalysts, basically any of the methods that we and many others in the community use to break down plastics, those small molecules, those additives, those co-monomers, all of those are going to come along for the ride. And that is one of the key challenges, I think, and still to some extent an unanswered question as to what is the impact of all of those sorts of dogs and cats or witches brew, as you called it, in terms of being able to repolymerize this. How pure do we need the monomers to be versus all the other stuff in there? I think those are open questions, and we and many others are trying to address those now.
If you like feedstock for you, I don't know, it would have to be incredibly specific, I think, in order for you to really make a robust way to recycle it. So like if I'm sending you PET from, soda company A, but then I send you what I think is PET from like, beer company C, how different would the feedstocks to you be? Again, because of all the different chemicals and enzymes and things like that that are put into the different plastics. Like,
right.
They all fall into the umbrella supposedly of like PET, but how different are they?
Yep. So I can't necessarily answer in a quantitative way how different they are, but I can say that kind of the beauty of using some of these deconstruction technologies like chemical catalysis or enzymatic catalysis is in many cases that we and others have looked at in the literature, in the community, I should say, there's not a massive impact on the process. And I think a lot of these processes that, again, we and others are developing will be sufficiently robust to be able to take in mixed feedstocks. And the beauty of enzymes, for example, is that they're extremely selective. They're going to go after the ester bonds in PET and leave everything else alone. There is an open question of, will all the other stuff leave the enzymes alone? And that certainly I don't think has been necessarily answered as well as it needs to be yet. And so, but again, many folks are working on that in the community, as they should be. And certainly with the substantial global ramp up in government and philanthropic funding in this space, many of those questions are starting to be asked and answered as well.
Yeah, do you think it's a pipe dream to be able to go to a landfill and empty it out, recycle a lot of the material there, or at least the plastics component, let's say, the ones that you're working on? Or is that still economically and, biochemically or chemically a long way away?
Yeah, I think a lot of it will come down to economics, right? And how expensive, and like you alluded to already, how expensive is it to go mine landfills and remove plastics? For example, there are companies that are paying for recovery of ocean plastics now to do various types of recycling and upcycling. For example, like Ghost Gear from the ocean. There's at least one company that I know of that is recovering nylon fishing gear and paying for that and using that as a feedstock for recycled nylons in the marketplace today. And so I think that, and kind of the same analogy with landfills, at least in landfills, of course, everything is static, right? It's all sitting there. I think it's really going to come down to the economics, though, of sorting. And that actually is kind of maybe a segue into another technology. Rich, if you're okay, I can tell you a little bit about mixed plastics and how we're trying to address the mixed plastics problem, because Because, for example, if you do want to go fish out plastics out of the ocean, if you want to go fish out plastics out of the landfill, right, and especially plastics that are already being sorted today, right, when people wish cycle, when they put in things into the recycling bin that the materials recovery facilities don't want, those are being basically lumped together like polystyrene, PVC, basically things that don't have recycling or resin identification codes on them. And so that sorting is an enormous challenge in plastics recycling today, right? And so what we are working on is, are there ways to not sort basically physically plastics from one another? And many plastics, especially in packaging materials, are multi-layer films of different plastics, right? Like your chip bag, for example, has a bunch of different plastics in those multi-layer films. And so we are working on technologies that use oxygen and very simple metal salts to break down mixed plastics. And there you definitely, because you have different chemistries of those plastics and you're using an oxidative or oxygen dependent process, there you definitely get your witch's brew of different compounds when you break that down. But the cool thing about that, I think, is if you have a mixture of oxygenated compounds, biology is extremely good at cleaning up those witch's brew. In the soil, when there's a lot of different carbon sources around, bacteria and fungi in the soil, their objective is to make more of themselves, and so they want to go after every organic molecule they possibly can, right? And so they've developed all of these metabolic pathways to be able to eat lots of different food sources. And what we're doing now is we're taking mixed plastics and we're using an oxygen-dependent process to break all of those mixed plastics down. We make a mixture of products from that, and then we have engineered an organism, a bacterium in this case, from the soil to be able to assimilate all of those different breakdown products from mixed plastics and make a single product from it. And I'm really excited about that idea of a big hammer. You use a big hammer on mixed plastics and you break them down. Now you've got small molecules. You can feed those to an organism and make a single product. I'm really excited about that idea. I think that potentially could get some traction to be able to avoid sorting and things like this. So
yeah, no, that's really cool that you can take multiple types of plastics and combine them into one useful product. What are the trade-offs between enzymatic action and bacterial action?
Yeah, great question. So enzymes, of course, cannot make more of themselves. They can't replicate like a bacterium can, for example. The enzymes that we work on for PET breakdown, for example, they can break down polymers really effectively, like PET polymers, I should say at least. And organisms, to my knowledge at least, have not been reported to do that in an industrially relevant fashion. Although at least one has been reported, Ideonella sacchiensis, which was reported in 2016 in a paper in the magazine Science, to be able to break down PET, but it takes many months to be able to do that. And so that's sort of the trade-off. The enzymes, if you apply them in an industrial setting, potentially can break down PET in just a couple days. Whereas if you applied like that Ideonella sacchiensis soil bacterium discovered by a group in Japan, it would take months to break down PET.
Yeah, what about systems where you do an initial treatment with a certain enzyme that unlocks things to a point where bacteria then take it, or back and forth?
Exactly. That's exactly what I was going to go next, is the cool part about combining, a depolymerization step, so a breakdown of polymers. That can be catalytic, it can be just with heat, it can be with enzymes. That unlocks these extremely big molecules that are polymers or plastics, right? That unlocks them into little molecules that then a bacterium is able to eat. And bacteria are really good at eating little molecules, or small molecules, but not so good necessarily yet, at least that have been discovered at breaking down and then consuming polymers all in one step. And so that's the idea that we're trying to apply for mixed plastics. Use a big and fast chemical hammer, break down mixed plastics, make a mixture of small molecules that bacteria will eat as a food source, and then engineer those bacteria to eat that and convert those products, those carbon atoms in the mixed plastics, into something useful for us.
Okay. Yeah, the hybrid method seems to be, I guess that'll be the future. Has anyone thought about putting, I guess I'll call it like a keystone molecule or bond or whatever it is or feature inside of plastics so that they deliberately can be radically or quickly disassembled by certain enzymes that maybe you guys would create or other industry would create?
Yep. That is a great question. And that is the other part, the sort of the second mission element of the BOTTLE Consortium, is we, and again, others in the community are, of course, working on this too. This is a large global effort. This concept of redesigned plastics, I think, is really important, right? The plastics that we all use today as consumers, right? All of those came from and were byproducts of the petrochemical industry, right? They can make ethylene. They wanted to know what to do with it. They discovered polyethylene. They can make propylene. They wanted to know what to do with that. Polypropylene was discovered. The same with nylon. The same with PET. The same with rubber, et cetera, right? With Bakelite, all of these things. They were products that were available, and incredibly smart chemists and engineers and researchers in general put together these amazing materials we know and love, but they were thinking about it from the perspective of, we have these molecules, what can we do with them that would be valuable? What we have is, I think now, as humankind, is an opportunity, given that those plastics were designed not with the end of life in mind. They were designed with merely their function during lifetime in mind. But now I think because of the environmental burden of both plastics manufacturing and plastics waste, humankind has realized we need to start over as well. And so that's where this concept of polymer redesign, or making polymers that are recyclable by design, I think is really gaining a lot of traction. And we and again, others are working on how do we make, say, your plastic bottle or a plastic film that goes over food at the grocery store, or a snowboard or a surfboard, car parts, or a wind turbine blade, or your keyboard, or any plastics that we use today. How do we make them out of building blocks that come from bio-based sources, and then make those plastics where they have the same function during life, during their lifetime, but also at the end of life can be completely recyclable? And we, and again, a lot of people in the community are working on throwing as many things at the wall as possible, figuratively, in terms of being able to propose these building blocks, put into these new polymers, and then compare it to the incumbent materials that we use today. Then figure out, how do we reduce cost? How do we reduce environmental burdens? How do we set up the recycling infrastructure for these redesigned polymers as they come into the market? Does that make sense, Rich?
Yeah, no, that makes total sense. One thing that came to mind is, again, in regards to microplastics. So I've asked a lot of researchers that deal with microplastics, has anyone modeled, I'm picturing like a plastic bottle in a container that's being sloshed around with a light source that emulates the sun, and, maybe some salt in the water. And again, modeling how fast and how long it takes various plastics to break down into microplastics. I know that's not the focus of this, but do you have any insight into how long and how fast and how difficult those processes are because of the work you guys are doing?
Yeah, that's a great question. So we definitely are looking at and actively collecting plastics, for example, from U.S. rivers, near where they enter the ocean. And we are attempting to figure out, when a plastic entered a river in the United States and it gets to basically the mouth of that river going into the ocean, how much breakdown has already occurred, and likely, those days to weeks to months that it took to go from, point A upriver to the mouth of a river where the plastics would enter the ocean. And, I think there are many folks who are much deeper experts in this than me, but I think the general consensus is that the jury's still out in terms of what type of polymer it is, what its surface area is, how big of a chunk of plastic it is, and then what environmental conditions does it see? Does it get in contact with sand where it would be undergo a lot of abrasion? Does it, like you said earlier, is it exposed to natural light, to UV radiation? I think that there's a lot of factors that play into the generation of microplastics and nanoplastics that are extremely poorly understood still, and there's fortunately a lot of people working on those types of things in the community. And the other part of that equation too is all of the small molecules that are present in plastic rich that you mentioned earlier. Those can leach out, for example. They will get into water, they'll get into the soil, and what the impact of all of those small molecules is on the environment, I think is also still, there's a lot of dimensions to that needs to still be understood.
Yeah, I guess there could also be, some nice point source filtering. Like I'm imagining a, washing machine or dryer.
Absolutely.
And there's a filter with some of the enzymes you guys have created that sits on the outlet.
Yep.
So it breaks these things down before they even get into the water. Or,
absolutely.
A bottling plant. Again, all their effluent, they're treating with your enzymes and bacteria and all that to make sure that, when stuff leaves the plant, it's not nearly as bad as it otherwise would be.
Yeah, exactly. I think that's where this idea of complementarity is really important, right? It's not like any of the technologies we're developing are intended or even should replace traditional recycling today, but they could certainly augment and be a complement to, for example, all the stuff that gets sorted and still put in landfills, or all the stuff that gets basically produced as fines or byproducts of these recycling processes. I think that's where technologies like that we're focused on for today's plastics can really be applicable. Absolutely.
Maybe one more project you're working on? Anything else really interesting?
Yeah, so let's see here. Yep, so another key aspect and an area of research for our team here at NREL focuses on conversion of the plant biopolymer lignin. So lignin is an amazing polymer, and it's in all terrestrial, or in most terrestrial plants, especially trees and grasses and food crops and things like this. And so lignin it was thought to evolve about 470 million years ago in plants, and it's what allowed plants to be able to stand up. Basically, lignin adds a lot of structural integrity and rigidity to plants when they're growing. It took fungi about 70 million years to catch up to be able to break lignin down. And so that 70 million years of sort of geological time scale where trees and plants were producing lignin in a terrestrial context between when it could be broken down by microorganisms when plants died, is when most coal and petroleum essentially now deposits, of course, that we are still accessing were really deposited. And so lignin is also an incredibly good pathogen defense for plants because it's a random polymer, unlike polysaccharides like cellulose, which is another main component of plants. Lignin is not regular. It's not a single building block. It's multiple building blocks. It's incredibly complicated, and it creates this barrier for fungi trying to degrade a plant. Or when a cow is eating grass, the reason it has four stomachs and chews its cud is because lignin is basically in the way of getting to the cellulose that, for example, ruminants need to make sugar. Then they can use that as a food source. And so we've been working in our group now for 10 years or so on the development of how do we basically make valuable things out of lignin. This has been a problem over the last century. There's literally a century of work that's gone into making money from lignin. And there's a very, very famous quote that says you can make anything out of lignin except money. And so in that vein, we've been combining, very similar to the plastics problem. How do you combine on this recalcitrant polymer from plants, a catalysis step that's fast, it is oxidative, and it breaks it down to small molecules, a witch's brew of small molecules from lignin in this case. And then we also feed that to a microorganism, and now we're able to make a single product from a heterogeneous polymer that is a waste product of pulp and paper processing. It's a waste product of biorefineries, and it's definitely, there's a lot of available lignin around the world that we can be harvested every year. And right now it's just simply burnt. And so we're able to make biochemicals out of it now and biofuels that potentially could be used in sustainable aviation fuel or could be used in those recyclable by design polymers.
So you said lignin is random. Does it just mean it has like irregular domains in its structure, or how do you compare it to, let's say, cellulose?
Yeah, cellulose is built out of one molecule, and that's glucose, right? And so it's a long chain of glucose molecules all connected together, and those chains then pack into bundles, and that's how cellulose is put into plant cell wall in these long polymer chain bundles. Lignin, on the other hand, is connected by it comprises multiple building blocks, and so instead of just glucose now, you've got multiple building blocks. They're all aromatic compounds, and then they're connected together through different bonds, different type of chemical bonds. And so cellulose has one bond, it has an ether bond in it, a beta glycosidic ether bond. Lignin, on the other hand, has carbon-carbon bonds, carbon-oxygen bonds, and different carbon-carbon bonds and different carbon-oxygen bonds. And so it's definitely a really complex random polymer. And that's why nature has had such a hard time breaking it down. It took 70 million years for fungi to evolve the ability to break lignin down. And even now, it's still, of course, very slow.
So how far along are you with the lignin project? Is it, how much do you understand of it, or what's left to figure out? What do you want to do with it?
Yeah, absolutely. So we have two different directions going on in lignin now. One is related to the production of sustainable aviation fuel. And so working very closely with a group at MIT in chemical engineering, specifically the group of Professor Yuri Roman, we have been able to, between NREL and MIT, take lignin and then fully remove all of the oxygen from lignin in a process-relevant, industrially relevant way. And the molecules that you then derive in that deoxygenation step, in about 80% or 70% of those molecules are right in the jet fuel range. And so this is a way to potentially, again, augment or aid in the production of sustainable aviation fuel and to fulfill another part of the portfolio of molecules you need in sustainable aviation fuel, which today mostly comes from like waste cooking oil and ethanol. And so this is another part of the chemical puzzle that you need for the production at scale of sustainable aviation fuel to decarbonize air transport. That's one direction we're going, and we're really excited about that. The other is, again, using a fast catalytic step to break lignin down. We make a mixture, and then we feed that to an organism. And we can make molecules, for example, that can go into better nylon materials, for example. We've also made a replacement for a PET bottle that, instead of lasting, say 500 years if it gets out into the soil, we've done soil trials with the U.S. Department of Agriculture, Agricultural Research Station in Albany, California, and shown that instead of 500 years like your PET bottle would last, this bottle built out of lignin-based building blocks would only last 5 years. But it has all the same properties as all of your PET does today. And so it could also be, not only, if it does escape to the environment, more easily broken down, but it could also be much more easily recycled. And Rich, that goes to your point earlier, putting in sort of Trojan horses in your polymer to be able to more easily recycle and break them down in a recycling context as well.
Oh, has anyone gotten far enough to make like a lignin bottle where you put drink in it and drink from it?
Yeah.
And test it?
Yeah, great question. So we've made 20 kilograms of this polymer so far, and we are working with a university now to make bottles from it. So that's active work that's going on now.
Oh, very cool. Yeah, what are you going to call it?
Right now it has a very boring name, which is the name of the polymer itself, which is polybeta-keto-adipate coterephthalate, or PBCAT. And so we're trying to figure out how to come up with a catchier name than PBCAT. So
that would last, it's estimated to be about 5 years?
Yeah, so the soil trials that the folks at the Ag Research Station in Albany did, they compared it to PET bottles, which are projected to last about 500 years, and they showed that, if, again, escape to the environment, biodegradability is not a solution, right? It's merely a safety net, and in this case, it would be about 5 years for degradation in the soil of this material.
That makes me wonder, how did estimates come out? I don't know, were they just guesses that, a plastic bottle can last thousands of years in the environment, or 500 years, who did those estimates? Because that organization or company or person should then have an estimate on how and why these things break down in reality.
Yeah, that's a loaded question. I'll preface everything with again, those are really complex questions, and there are ASTM methods to measure lifetimes of plastics in various environments: freshwater, saltwater, in the soil, in the anaerobic soil, in aerobic soil, in an anaerobic digestion system, in a composting system, in an industrial composting system. And then those are all sort of bottom-up ways, right? Like, I can go to the lab and we can test those in the lab. And then there's the other direction where it's more top-down, where folks are collecting materials from the environment that have been in the environment for, again, weeks to months to years to decades, and then looking at the breakdown of those. And I think it's a lot of this is an amalgamation of a lot of these things. And if you look at the ranges of time for breakdown, the ranges on conventional polymers to break down in the biosphere is enormous, right? I mean, many, like multiple logs or multiple orders of magnitude in terms of time to break down. And so I think, again, it's not a simple answer of a PET bottle takes 500 years. It really depends. Context really matters.
Excellent. Well, very good, Greg. It's been a really good call. What's the best place for people to find out more about your work and NREL's work? Where can they go?
Yeah. So certainly we have a website for BOTTLE. It's www.bottle.org. That describes the U.S. Department of Energy funded research that we work on from a plastics upcycling, recycling, and redesign perspective. And then one can go to www.nrel.gov to find out more about the work that NREL is doing in energy efficiency, renewable energy, including the things I talked about today.
Excellent. Well, Greg, it's been, like I said, super interesting. Thank you so much for coming on the podcast. I appreciate it.
Yeah. Thank you so much, Rich, for the opportunity. I really appreciate that.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.